First, we're going to review a little bit about integrals in Calc 1 very quickly. Calc 1. If we have an integral of a function with respect to x from a to b, and the function happens to be positive, then we are finding an approximation to the area. Well, this would be the exact area, but initially we start out with an approximation by splitting this into rectangles. I want to emphasize that this would be the case if the function is positive. If the function happens to be negative at some points, then the picture doesn't work as good because we will have negative products. For the sake of this, assume this is x1, a will be here, x2 would be there, but it doesn't have to be there. Actually, let's move x1. Let's put x1 in the center. x1 center, x2 center, x3 and center, x4. So we start out by multiplying the outputs, corresponding outputs. Let's label the outputs as y1. So the height would be y1. The height of this would be y2, y3, and y4. The distance between the beginning of this subinterval and this and the same subinterval, the beginning and the end, is going to be labeled as delta x, and it will be the same across. There's a few different ways to define an integral. We can define it for now as assuming that they're all equal, those distances being equal, and assuming again that we're using the midpoint, but we don't have to use them all equal. There are some other restrictions we would have to impose. So making the subintervals equal makes things a lot easier. And we don't have to use the middle point. We could use the end point or the first point, or actually different points on each subinterval. But again, we're going to use the midpoint for now and call this the midpoint rule. So the way to approximate this integral is by first adding x1 multiplied with delta x, which is this distance. X1 would be the point, the actual input. So for instance, if the origin was here, this would be a number far away from 0, which would have not necessarily anything to do with this length. So we want to multiply delta x base times height to get this product. So y1 times delta x would give us this product. If we add y2 times delta x, I'm kind of doing this as height times base instead of base times height, because traditionally we do write down delta x as on the right side of the function. So height times base, height times base, height times base, so plus y3 delta x plus y4 times delta x. That is the sum of those 4 rectangles. And then we can factor out the delta x. So we have y1 plus y2 plus y3 plus y4. Delta x, that is another way to rewrite the sum of those 4 rectangles. The areas, of course, of those rectangles. And there's a shorter version, the sum of the yi's from I equals 1 to 4. Delta x will be the sum of those 4 rectangles. If we had n rectangles, so this is the sum of those 4 rectangles. By the way, I just noticed I did not use the midpoint here. The picture would be a little shorter for this rectangle, and so would be for this rectangle. Yeah, we have to adjust that. I'm going to do an example which will make this more clear, an actual concrete example of using the midpoint rule to approximate the value of this integral, the actual value of this integral. Right now, I just want to give the general idea of what's going on. Um, if we have n rectangles, so this would be the case with 4 rectangles. If we have a generic n rectangles, then we would have the sum of n of those. And so we have the sum. The only difference here is that we are going to be changing I the n value instead of being 4 will be n yi delta x. So this would be the sum of all of those rectangles. So that's the setup of how we get started coming up with this. And this integral will be actually the limit of that sum of yi's from I equals 1 to n delta x as n goes to infinity. So that is the way we define a definite integral. There's a lot packed in here. We're assuming that the function initially is continuous so that there's no issues with using also this kind of subintervals. There's a lot of stuff going on, but this is the gist of it. This is the main idea that is going on. So we're adding those, and we take the limit as the number of the pieces we're adding increases with no bound. If some of those numbers are negative, if the yi's are negative, then the product would be positive times a negative. So some of the parts would be negative, and we would have, in quotation marks, a negative answer. So for the time being, we assume that the function is positive, so we can think about area, but we don't have to have positive functions, obviously. Anyway, this is just a review. Let's do a quick example still within Calc 1. So all of this is Calc 1. I'm not doing Calc 2 yet. So let's approximate. I said Calc 2, I meant multivariable calculus, by the way. Approximate the integral from 0 to 1 of x squared dx by using a midpoint rule with n equals 3. So we're going to take 3 subintervals of this function. So this is just a regular x squared, so it's a regular parabola from 0 to 1. And we're going to split this into 3 pieces. And since we are split into 3 pieces, that means that each one of the subsegments will have a length of 1/3, because the total length from 0 to 1 is 1. So if we split into 3 pieces, each length delta x equals 1/3. We're going to take the midpoint here, which would be 1/6. 1/6. The next midpoint is going to be 2/6, 3/6, which makes sense, 3/6. And the next midpoint will be at 5/6. 5/6. So that means that the corresponding heights are going to be, since we're squaring, this is a simple function. So if we're squaring, the output of 1/6 will be, 1/36. So that is the output here. The output of 3/6 will be 9/36, because we're squaring 3/6. And the output corresponding to 5/6 will be 25/36. So let me put out the output. So we have 1/36 times 1/3. So height times base, that gives us the first rectangle, plus 9/36 times 1/3 plus 25/36 times 1/3. The 3 times 36 is going to be 91/8. And then we can add the numerators. 1 times 1 is 1, 9 times 1 is 9, 25 times 1 is 25, 25 plus 9 is 34, 35. So we will end up with this sum equals 35 over 108. And that is our approximation. Um, so this is a bunch of 3s and 2s and 7 and 5. So we cannot simplify that. That is the exact approximation to this integral. 35 over 108, by the way, 35 divided by 108 is about, so this is an approximation of that integral. It is about 0.32474. So I'm just using a basic calculator to figure this out. We do know the exact answer, by the way. From calculus 1, we know that the integral 0 to 1 versus x squared dx is x cubed over 3 from 0 to 1. And that, of course, is going to be 1/3 minus 0, which is 1/3, or about 0.33. So this approximation is reasonably close to the actual answer. It's not the answer, but it is close to the answer. So just be aware that whenever you have an integral, if the worst comes to worst and you wanted to find some idea of how to figure out its value, you can always split it up into some pieces, a few of them, start working, cranking the numbers out, and add them together, multiply, add together, and boom, you get an answer that is not too far from the actual answer. We can always do that, even with really ugly, terrible integrals. You can always get an idea of what the solution should look like. All right. Let's label this as examples 0 so that we can refer to it if you have questions about the video. So this guy, we're going to call it example 0. All right. So now let's go to multivariable calculus. Multivariable case. All right. So first, we're going to divide. We're going to work, instead of having a straight, nice segment over which we're going to integrate, we're going to integrate over a nice, initially, straight rectangle. So this is a rectangle on the XY plane. So the origin is somewhere back here. And so we're going to go from A to B on the axis. So pretend this is the x-axis. Well, no, pretend this is lined up. This is parallel to the x-axis. So the x-axis might be here. This could be off. And then from here to here, we're going to go from C to D. So that is our generic rectangle. This rectangle will be labeled as R for region. R for region. And we're going to split this rectangle into pieces, into a few pieces. So this. So we're going to assume we have M. Oh, and we're going to split it down this way and across. And we don't have to have exactly the same number of rows as columns in this case. So we can assume we have M of those and N of those. So we have a total of M times N sub-rectangles for a total of Mn. So M times N sub-rectangles. There we have it. So this is neat. We're going to use the midpoint rule again. So the midpoint rule says that we're going to pick the middle of the rectangle on each one of the sub-rectangles. Similarly as in here, where we pick the middle of the subintervals, whatever they are. We're going to label this we're going to label this guy as, I guess, See, this guy has an X and a Y coordinate. So I guess we can call it X1, Y1 point. There should be a comma in between. And then, so we're gonna keep the same X and move the Y. So this point, the second point will be X1 because we're still going out this way towards us. But then to the right, we're moving past the Y1. So now we're gonna be Y2. So we're gonna have X1, Y1, X1, Y2, X2, Y2. I'm sorry, X1 still, Y3, X1, Y4. So let me turn this and make sort of a table here. So we go from A to B, C to D. We're going to split this into 3 across and 4 this way. And we're going to have xi comma yj values. But this box is rather small, so I'm just going to put the indexes. I hope you don't mind. So this is a table of the indexes ij, because it's a lot of writing to put x1, y1. So I'm just going to use a shortcut and a shorthand. I'm going to label this as 1, 1. So this would be 1, 2, 1, 3, 1, 4. Remember, those are the I and the J values of this point, which would be in the middle of each one of those rectangles. We're going to do a concrete example so you can see how this works. So then we have 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4. In this case, we have M, which is 3 of them. So M would be 3 and N would be 4. This is a more generic, we could have that yada, 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 um, you know, more rectangles one way and more rows the other way. But here more concretely, we have 3, we're splitting the X interval into 3 subintervals and the Y interval, whoops, I didn't mean this to be C. C goes from C to the Y interval into 4 subintervals. And that's how we obtain, in this case, 12 sub rectangles. All right. So the double integral, we're working with a double integral of a function x, y with respect to the area. So this is with respect to the area as opposed to in Calc 1 with respect to the input. So with respect to this line. Now we're going to do it with respect to the area over the region. It's, in this case, it is a little hard sometimes to describe the region. So we just label R, the region where we are integrating, and we, in somewhere else, we are defining what R, the region R is. Yeah. So for instance, back here, if this was just a generic interval, well, a fixed interval I suppose using this notation here, we could rewrite this as an integral over the interval I, where somewhere else it is got to be shown what I, the interval I is, and I'm using I for interval, f of x dx. So I suppose we could write it this way. We don't. We reserve this kind of notation for multivariable calculus, but I suppose we could do it that way too. Okay. So, so how do we go about getting this or defining this double integral? This is a double integral. Double integral. And how do we define it? All right. So back here, the way we define the regular integral is initially by taking the heights, those heights, multiplying them with the base, and then adding them together, heights times base, so that gives us these areas. And then we have a sum, and then we take the limit of the sum. So we're going to do something similar here. I'm going to draw a new picture here. So, well, this picture should be, so this is again a rectangle, A to B, and then from C to D, and we're splitting this into sub-rectangles, and then there's going to be a function up here. I'm not going to draw the function yet, but the midpoint here is going to correspond to an output, which we're going to call Z, just as here we had X1 and an output Y. Here we have an input X1, Y1, and an output Z11. This output corresponding to this input, this XY value, is going to be Z, we're going to label it as Z12, corresponding to the index 1, 2. And then this one, which may be lower, who knows what the function looks like, will be Z13. And let's say this is lower yet, Z14. There should be a comma really between those two, because otherwise those read as 11, 12, 13, 14, but that's not what we mean. We mean 1, 2, in this case, 1, 1, 1, 3, 1, 4. But I don't want to fill this in with a bunch of little commas. So then we have another output, say Z21, another output, say Z31, and so forth, each one of those. So then we don't necessarily connect them, but we have some kind of surface up here, and then each one of those is going to have its own output. Okay. So how are we going to, what are we going to add together? We back here, we were doing areas, the area of this rectangle. So it makes sense to now use volumes. So for each one of those sub-rectangles, so there's a little sub-rectangle, we're going to have an output, and we're going to build a column. There we go, a column as opposed to a rectangle. This is supposed to be straight. I'm not going to redraw it, but the area in the bottom, and how do we know the volume? What is the volume of this? Well, you guys know it. It is length, depth, and height multiplied together. I missed to tell you what the length here will be. This would be delta y, because those are C and D are numbers relative to y. A and B are numbers relative to x. So each one of those sub lengths are going to be delta x's, delta y. Yep. So we have delta y, delta x, and then the height is going to be each corresponding z. Whoops, sorry to move this out of the viewing area. So we have delta y, delta x, z, I guess, I, j, depending on where we are. So the volume is going to be similar to the area. Remember, we multiply y times delta x. So we're going to multiply z times delta x times delta y to get the volume of this column. So what we're going to do is we're going to add Z11 times, actually, I'm kind of getting ahead of myself. Let's label each one of those as delta A for an increment in area. So this is an area, and it is going to be the same as this area, which is going to be the same as this, whoops, delta A. Yeah. So instead of writing dx or delta x, delta y, I'm just going to put d delta A, which is, and by delta A, we mean, yeah, I might just as well write it here. Delta A, we mean delta x times delta y. So this is the volume of the first column up here. Then we're going to add the volume of the next column on our right. So that's going to be plus Z1, 2, delta A. And then the third one, Z, oh, there's two more to go, so I'm going to go to the next one. Z1, 3, delta A plus Z1, 4, delta A. That's just for the first row. Then we got to do that two more times. And two more rows. I just want to give you the idea for now. So each row can be written as using sigma notation. So we could have Z1J, 1J, as J goes from 1 to 4 in this case, plus, oops, I missed the delta A, plus sigma from J1 to 4 of Z2J delta A plus sigma from J equals 1 to 4 of Z3J delta A. But these are very much the same kind of sums. The only thing that we're changing is that we start with the first row, second row, third row. So a sum, we have a sum of sums where we have the same kind of pattern. I didn't want to move to a new, so I'm going to try to squeeze it here. So this is the same thing. This sum of sums is really the sum of Zij delta A as I goes from 1 to 4, rather as J goes from 1 to 4, and as I goes from 1 to 3. There we go. So we can add all of those columns, the volume of all of those columns, by adding the volume of the rows, and the volume of the rows in turn, it can be found by adding the volume of the columns on that row. That's what we're saying here. So add the rows, the volume of the columns of the rows. Once you have that, then add the volume of all of the rows, and that gives you an approximation of the volume of this surface. Okay, so here's what I want to arrive to. So the double integral with respect to the area will be the limit of the double sum. That's why it's a double integral, because it comes from a double sum of f of xi, yi, delta a from j equals, I meant xi and yj, each one it should have its own index, 1 to, okay, so the y's go in general to n, and the x's go, and we have m of them, there's the m, from I equals 1 to m. And we have a double limit really, as m goes to infinity and as n goes to infinity as well. Whoa. So this is the way we formally define. Well, this is not completely formal because I'm not giving more information about the function. We can assume that the function is continuous, for instance, and then this will work really well. But this is somewhat formal definition. It is a limit of a double sum. Again, it is a somewhat formal definition of a double integral over a rectangular region. We're gonna, in the next video probably, to define a double integral over a region that is not rectangular necessarily. Now, our example 0 was an approximation of this. We are going to do an approximation as an example 1. It is going to be an approximation approximate um, the double integral of x squared plus y squared with respect to the area um, over the region. And we're gonna say what the region is. Um, let's keep things a little simple for purposes of this. Yep. So the region, with the region being the set of all the x, y inputs, so that 0 is less than or equal to x less than or equal to 2, comma, a 0 is less than or equal to y less than or equal to 3. So that is the region of this example. Using midpoint rule, with, let's make sure I'm using the correct m and n. So m is going to be the splitting of the x interval. This is the x interval with m equals 2, n equals 3. Okay, so this is the function. So this is what we are doing. We are familiar with this function. It is a paraboloid. Z equals x squared plus y squared. By now, we've done several examples of this. So if you go 2 units, 3 units, so 2, and then 3 across. Then we have a paraboloid. Remember the shape of the paraboloid. So this is far. So the height of this is going to be quite a bit, 9. And then this is 4. So it's going to be lower. I should have given myself more room because this is going to be, the height of this is going to be, by the time we get to 2 and 3, we're going to end up with 9 and 4, 13. So this is going to be much higher. Let me lower this. So pretend this is 4, 9. And so that way I can squeeze the 13 here. There we go. And I think this is going to go, yep, this way. So this is parabolic. And what is the 13 over here? So this is probably going to go this way. So there's a solid, which is, this solid is really, pretend you got your regular paraboloid. And if you take a saw and you cut across this way, and then you go 3 units and cut this way. Yeah, so this is another way to, oh, I meant here. This is gonna cut here, and then my rectangle here let's pretend that's it. So this is the picture. This portion under the paraboloid is what this describes. And we want to approximate the volume under the paraboloid. Mind that this is the volume under the paraboloid, not inside of the paraboloid. Okay, so how do we go about approximating this? So we need 6 columns because we're going to split the interval. Okay, so let's go this way. We're going to split the interval from 0 to 2 into 2 parts, from 0 to 3 into 3 parts. By the way, each one of those is going to be 1 unit, 1 by 1 unit square. So the delta A is going to be nice. It is going to be 1 by 1, which is 1 square unit. So the base of each one of the rectangles will be 1, which is going to make this a little easier to work with. The midpoint here, now remember, this is the x-axis and this is the y-axis. So this is the x-axis and this is the y-axis. Yeah, let's put the x over here. And this is the origin. All right, so I need to figure out what this output is, or this input rather. This is a half, a half, a half, a half. And this is a half, three halves. One half, three halves. One half, five halves. That. And then we're going to have three halves, three halves, one half. That's the midpoint here. Three halves, because this is from here to here is two. So 1.5 is three halves. And then, oh, three halves, three halves, three halves. And then the same thing here, three halves and five halves. Those are the inputs. But what about the output on each one of those rectangles? Well, we got to square each one of those according to this formula, to this function that we're integrating. So that is a quarter plus a quarter, 1/4 plus 1/4. And that is going to be a quarter plus 9/4. And that is a quarter plus 25/4. That is 3. So that is 9/4 plus 1/4. 9/4 plus 9/4. And then 9/4 plus 25/4, because we're squaring each one of those and adding them together. So the volume of the column, there's a column going up this way. The base is 1. So here's the base. So we're splitting this into 6 pieces. So the volume of take the midpoint, and we're going to build a column here. It's going to get too messy if I try to draw that. But there's a column, a short column here, and the columns get higher. By the way, this is a half. I'm going to draw a new. So this is a table of the outputs relative to. So the output here is going to be 1/2. That's 10, 5 halves. That is going to be 26 divided by 2 is 13 halves. 10, 5 halves, 9 halves, 34, 17 halves. So those are the heights of the rectangles that go with the midpoint using this function. So a half, if you go in those two directions, 5 halves, so low, higher. This is next and high, that's taller, and this is taller. So it's pretend you got a bunch of buildings right next to each other, adjacent to each other, of different heights, and those are the corresponding heights. So the volume of this, so these are the z values, the ones I'm showing you for each one of those rectangles. Each one of those is going to be multiplied with 1. So that makes things really, really easy. Multiply 1/2 times 1, that still gives you 1/2. 5 halves times 1, that gives you still 5 halves, and so forth. So if I want to know an approximation, all I have to do is add those together. So all of them are halves. 1 and 5 is 6, and 13, 19, and 5, 24, 33, 50. Ooh, 25. So the sum, the approximation, so the double integral over that region we defined of, I was going to put f, but we know the function x squared plus y squared with respect to the area is approximately 25, if I'm not mistaken. So 17 and 13 is 30. 1 and 9 is 10, so that's 40. And 5 out 5 is 50, but all of those are half, so it's 50 divided by 2, which is 25. I did not say the double integral is 25. It is about 25. Wow. But now the question is, how do we know the exact answer? Because in back here in example 0, we were able to find the exact answer because that comes from Calc 1. We approximated and ended up with 35 over 108, which is about 0.324. The exact answer is 0.33. That's reasonably close to one another. But what about this one? What is the exact? This is an approximation using columns, just like back here we use rectangles. But that isn't, that gives us this, but that is not the exact answer. The exact answer is 1/3. So let's do that here. So we're still continuing with example 1. Still in example 1. Okay, so what about exact answer? Yeah, we're really curious. So what is the double integral of over that region over x squared plus y squared with respect to the area? How do we find it exactly? And we're going to use what is called an iterated integral. So we're going to change that into, this is a double integral. And so that is double integral. And we're going to change that into an iterated integral. The iterated integral is the integral of the integral of x squared plus y squared dx as x goes from 0 to 2. And then once we do that, we're going to integrate that answer with respect to y as y goes from 0 to 3. That's what is called an iterated integral. We usually don't write it this way with the parenthesis, but I want to emphasize that we have a nested integral inside of another integral, hence iterated. Again, we usually don't write the parentheses. You never ever see parentheses really. I put them for emphasis more than anything else. But then you're thinking, wait a minute, there's a y squared. Just like with partial derivatives, we treated the non-variable. So let me back up a little bit. The concept of variable is relative. So the concept of variable is relative. In some places, in some instances, we think of something as being variable, and in some instances that may not be variable. It depends. So variable is relative to a context. For instance, the example I always give is that pen moving. Is it moving? No, it's not moving. You're thinking, well, I can stare at it, and my eyes are not moving, so that seems to imply that the pen is not moving yet. But this desk is on the Earth, and the Earth is rotating around the world, and that's why we can. So is the pen moving? Well, relative to what? To the desk? No, it's not moving, unless I do this. Is it moving relative to the sun? Of course, because the planet is moving in its orbit, and not to mention that we are rotating. So there's a lot of motion going on with this pen, even though we cannot tell. So asking when something is moving, which is variable, is relative to something. So in this case, the variable is declared by the differential. So this guy tells us that the variable is x, and anything else is not a variable. So y is a constant. Once we finish that up, then this guy is going to be the variable, the y, and not the x anymore. Although by the time we get to the exterior of this double integral, or these two integrals, the x is going to be gone because the x is going to be evaluated from 0 to 2. All right, so let's go about that, doing that. So let's keep this 0 to 3 part out. So the integral of x squared, of course, is x cubed over 3 plus, treat that as a constant, so we have xy squared, using the fundamental theorem of calculus, from 0 to 2 dy. So this dy is waiting while this is happening. So this is the integral from 0 to 3 and then we plug in the 2. Having 0 helps because we know that when we plug in 0, we get 0/3, well, 0 cubed over 3, and 0 times y, whatever the value of y is, that's still going to be 0. So plugging in 0 will provide us with a 0 here. I don't have to worry about that because we're going to subtract it. All I have to worry about is the 2. So we have 2 cubed, which is 8/8 plus 2y squared. 2y squared, close the bracket, dy. Okay, so now this is a pure function of y, no x involved because that was already evaluated. And now we can move on to our next integral, the exterior integral. So that is going to be, according to the fundamental theorem of calculus, let's see if I can do it here on the side. So we're going to have 8/3 y, because that is a constant, plus 2y cubed over 3, close parenthesis, all of that evaluated from 0 to 3. 0 to 3. So whenever you have 0, double check that you're not going to have something that is not 0 when you plug in. Get into the habit of that, because sometimes you do get something that is not 0, such as when you have cosine of the variable or e to the variable, you plug in 0, you don't necessarily get 0, you get 1 in those two cases. So first I check, do we get 0 when we plug in 0? Yes, 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 yes. So I don't have to worry about this 0 because we're going to get 0. All I have to worry about is the 3. So 8 times 3 divided by 3, well, that's just the 8, plus 2 times 3, 3, 3, because that is, that we're going to have 3 cubed, so 3, 3, 3, but then we're going to divide by 3, so we had 3, 3, 3. After we divide by 3, we have 3, 3, which is 9 times 2, 18. And 8 plus 18 is 26, which is consistent with, so this integral is in reality, in actuality, equal to 26 exactly. Remember that volume that we drew before? Oh, I was going to draw it, but there's no point in drawing. The volume under this surface, this paraboloid, but above this rectangle, exactly above this rectangle, will be exactly 26. In our approximation, we got 25. Boy, this is almost weird, creepy that we are getting exact, whole numbers. Usually we get things like, 0.32, decimals. So we get 25, and for the approximation, which makes sense because 26 is not that far off, just like with our example 0, we got 0.32 and change for approximation, and the answer is 0.3333 and so forth. So that's how we find approximations of integrals. And I just show you how to find an integral. Let me try to squeeze the last thing I want to say about this before. Well, there's two things. So a double integral, as long as we are over a rectangle, mind, this has to be a rectangle. For general shapes, we're gonna address that in a future video. Of a function of two variables with respect to the area can be rewritten as the double integral. I said double integral for this. So this is iterated integral, f of x, y, with respect to x and with respect to y. Assuming that the rectangle is 0, 2 by, oh, I meant to say a, b. So that is on the axis, c, d. I want to do this more in general. So that would have been 0, 2, 0, 3 in our example 1. So this double integral is the iterated integral from a to b, for the x's, from C to D for the y's. And there's a theorem that says that if things are not too wild, this is the same as the iterated integral of the same function, dy dx. So you can reverse, with a rectangle, it is very, very straightforward. You can reverse the order of the interaction with no consequences. So we go from C to B, and from A to B last. And the theorem that there's, if you have a continuous function, then everything is going to be good. The theorem is called Fubini's theorem. Fubini's theorem. I'm not being completely formal with this because I'm not telling you all the requirements for the theorem. Continuity will do, but this is an explanation for the formal Fubini statement of Fubini's theorem. You can just go to any good book in calculus, and they'll have it there. One quick other thing I need to say about this is that is the integral is in Calc 1 or 2 is integral equal to area? And the answer is area. Well, there's too many questions. It depends. Area of what? You know, like if you have a parabola, is the area of the parabola? Well, no, it's the area under the parabola and above the x-axis. So you have to be more specific. Area of what? And the answer is yes, under the curve, if the function is positive. But if the function is negative, let's say you got a function here, this is the x-axis, then you don't get the area, you get the negative of the area. And if the function crosses the x-axis, you know, from here to here, for instance, then you don't get the area, you get the number you obtain from adding, well, this area minus this area. So sometimes, yes, we get the area. Specifically, we do get the area when the function is positive, and if what we mean is the area below the function and above the x-axis. With multivariable calculus, we have this similar question. Is double integral equal to volume? And the answer is similar. Well, it depends. If the function is positive, then yes. And you get the volume under the function, under the surface. If the surface is positive, then yes. But if the surface, so you get a surface here, you know, and then we get a corresponding nice rectangle on the XY plane, then yes, you get the volume. Nice. If the rectangle is there and the surface happens to be underneath, then it can happen very easily there. Ignore that part. There you go. Then you get, so positive volume, then you get the negative of the volume. And then the third case is, let's say you got your rectangle. So this is the region R, this is the region R, And then what happens if some of it is under, but then some of it is above, and then this crosses somehow. So the surface is really this surface that I'm shading. Do we get the volume? Well, it depends. You get the volume here, volume 1 positive, but then this is volume 2, which would be negative. And then when you add them together, you get the double integral. So do we get the volume? Under some circumstances, yes. Under other circumstances, no. Yep. And that's where we end this video.